Wait a second, I need to know algebra for this stuff? Oh, shit. Okay, welcome to chapter 18. We've got some good stuff coming our way in this video. We're going to have just a whole lot of formulas dumped on us right here at the beginning. We're going to have some of the most basic differentiation rules are now going to be accessible to us. They don't need to be memorized because they're in the formula book, but we need to be able to use them fluently. This might seem overwhelming at first. As I said, there's going to be a lot of formulas, especially as we progress throughout the chapter. But I promise, with a little bit of practice, this will seem as natural to you as addition. Because really, we're just learning a new operation, and the rules themselves are, for the most part, pretty straightforward. Really, the big one for this chapter is right here in section B, the chain rule. For right now, it's not going to seem like it's a huge deal because we're still dealing with pretty simple ones in the first few sections. But as we get through, you'll see that the chain rule really does pop up a lot. And what I found, at least, is most of the time when students ask me, hey, I got the wrong answer here, can you explain what I did wrong? I generally say, without hesitation, the chain rule. And that tends to be the mistake people make more often than not. So really focus hard on that one when we talk about it. All right, let's go. We're no longer using first principles. Now we're using some shortcuts. And if you did enough first principle examples, you may have started to notice some patterns. So here's a few very simple differentiation rules that we should know. First off, if our original function is a constant, this is obvious just from thinking graphically. If we have a constant function, then the derivative of that constant is going to be 0. The slope of a constant, of a horizontal line, is 0. The second one, this is our first real derivative rule. It's called the power rule. And this is really the one I meant you would have seen patterns of with first principles. If we have x raised to a power, its derivative is going to be that power multiplied by x to a power 1 less than it. So as in a quick example, if we had x to the 5th, its derivative is going to be 5 times x to the 4th. Something to memorize. Third one, scalar multiplication. So c here is a constant again. So we have c times a function of x. The derivative is just going to be c again times the derivative of x. As a concrete example, let's say we had 2 times x to the 5th. What that's saying is it means my answer is going to be 2 times whatever the derivative of x to the 5th is. And I know the derivative of x to the 5th is 5 times x to the 4th. So I multiply that by 2, and I get 10 times x to the 4th. So constants just kind of come along for the ride. And I'll have more to say about this rule when we get up to section C and we see the product rule for derivatives. But for now, let's just go with it. It's a nice shortcut. And finally, we have the addition rule, which is really an addition or subtraction rule. If we have two functions being added or subtracted, we can just take their derivatives separately and then stick a plus or minus sign in between them. So these problems that we're going to look at in this video, we should be able to do quite a few of them in our head in a matter of seconds. This one included, what is dy dx? That's asking what is the derivative of this function. We're just going to use the power rule on the first term, so that 2 is going to come down. It's going to multiply by 3 to give us 6. So that'll be 6 times x to the power of 2 minus 1, which is 1. Then we've got a minus. Then it's going to be 4 times the derivative of x. The derivative of x is just 1 times x to the 0, which is just 1. Whoop, don't look at all that. So yeah, 6x minus 4. The amount of time I took just speaking that out loud is far too much time. We should be able to get that really in like 1 second flat. All right, second, interpret its meaning. What does that mean, 6x minus 4? The book gives us kind of 2 bullet points to think about. First, this is the gradient function, the slope function for this curve. So we can find the slope of the tangent line to that curve at any point by just substituting that x value into 6x minus 4. Perfect. We could also think of it just in terms of instantaneous rate of change. of, as always, our dependent variable with respect to our independent variable. So y with respect to x. Okay, another two. The first one, in our head, in seconds, looking at it. The first one's going to be 15 times x to the 2 plus 12 times x to the 1 minus 3 plus 0. Did you get all that? Okay, you should be able to do it, again, even faster than I just said it once you guys start getting used to this. So think about what those steps were and recognize that you can do that all in your head. The second part, all right, maybe you want to rewrite this as our little friend is hinting at us down here. It's 7x minus x to the negative 1 plus 3 times x to the negative 3. So when I have x's in the denominator, it's better to think of them using negative exponents. And then from there, the rules are all the same. Now, once I see it in that form, I know the answer is going to be 7. And then it'll be plus 4 times x to the negative 2 minus 9 times x to the negative 4. Right? And again, that's all just power rule and then addition and subtraction. Super easy, yeah? Let's look at another one. Two things happening here. First, find the gradient function, and hence find the gradient at this exact point. Okay, the gradient function just means take the derivative. This is, again, x squared minus 4 times x to the negative 1. So its derivative is going to be 2x plus 4 times x to the negative 2. It is unnecessary to have all this work written down. You should be able to get from here straight to there. And then we just substitute in 2 into that. Gradient's pretty obviously 5. At the end of this video, I'll talk about how to do all this in the calculator, or how to do this part on the calculator. We cannot do that on the calculator, unfortunately. If we've got radicals, we just want to rewrite those as exponents as well, right? So that's going to be 3 times x to the 1/2 plus 2 over x. So this one's a little bit tougher. We're going to have fractions involved. But again, using the power rule, it'll be 3 times 1/2. So I've got 3 over 2 times x to the power of negative 1/2, because that's 1/2 minus 1. Plus, oh, I meant to write that as in that form, right? So it'll be minus 2 times x to the negative 2. If you want, in your final answer, you can rewrite your exponent form back into a root, but there's no need to do that. Over here, we got x squared minus 4 times x to the negative 1/2. So it looks like we're dealing with 2x plus 2 times x to the negative 3/2. And then, of course, we can rewrite that exponent into radical form as well. But I don't know. I tend to just use exponents in my work. It's really up to you how you want to do it. So those are our basic differentiation rules. Now let's get into the good stuff. Let's take a peek at the chain rule. We're in section B now. The chain rule is all about composite functions. So that's what we're going to have to be on the lookout for now. Stuff like this. The way that the formula book states the chain rule is down here. So that's just copied straight from the data booklet. I don't care for this format, so I'm going to write it out in a different way that I think makes more sense, at least to the beginner calculus student. But this is worth looking at because this does tell us something important. So they're writing their composite function. They're saying y is equal to g of u, where u is equal to f of x. In other words, they're saying y is equal to g of f of x. They're saying, therefore, the derivative of y with respect to x, So we're finding y prime, that is to say we're finding g of f of x all prime. They say that's equal to dy du. Why is it dy du? Well, because here we have y as a function of u. And then they multiply by du dx. Why is it du dx? Because u is a function of x. So think back. Normally we have y is f of x, and then we're using dy dx. So anyway, these fractions are excuse me, they're not fractions, I'm sorry. But these derivative notations that appear like fractions, they're coming straight from our definition of our functions over here, and it's the derivative of the dependent variable with respect to the independent variable. And hey, while we're on the topic of talking about these things not being fractions and all that, notice, if we were to cancel the du's, we'd have dy dx equal to dy dx. Why are they being multiplied? I'm not going to tell you. There's a formal proof you can look at if you're interested in. It's too long for the purpose of this video, and you don't need to know it for the course. You just need to know that this is true. But I said I don't like this form. I like to write it in a slightly different way. So here is how I would finish up writing the chain rule. Y prime equal to g of f of x prime is equal to g prime of f of x multiplied by f prime of x. That is, verbally, it's the outside function, or the derivative of the outside function with the inside function as its input multiplied by the derivative of the inside function. I think that's going to make more sense in the context of an actual problem, so let's do some. And we're going to see these written out the way that the book likes to do it, and then I'll show you how I would conceive of it myself. First one, y is equal to x squared minus 2x all to the fourth. So here's the book's method. They're saying y is equal to u to the fourth, so like there's something to the fourth, and then that something is x squared minus 2x. So we're going to calculate the derivative of dy du. That's like looking at this function and pretending it said y equals x to the fourth and calculating its derivative. The derivative of x to the fourth would be 4x cubed using the power rule. So we're going to write down 4u cubed here. And then we're going to write down the derivative of du of dx. That's like looking here and saying, oh, y equals x squared minus 2x. What's the derivative of that? Again, using power rule, it's 2x minus 2. So we've got that there. But then, since we know that u is equal to x squared minus 2x, we can input that for the u there. And our final answer can be 4 times x squared minus 2x cubed times 2x minus 2. That's one way to do it. Here's how I would write this down. And again, it's the same thing. I'm just kind of thinking of it in a slightly different way. Again, I look here and I notice that the outside function is to the fourth, and then the inside function is x squared minus 2x. So I just write down, kind of in one step here, I'm going to take the derivative of the outside function. That's power rule. So it's going to be 4 times a thing cubed. What is that thing going to be? Remember, it's the derivative of the outside evaluated at the inside, meaning this is just going to get copied down. And then we're going to multiply this by the derivative of the inside function, the derivative of that thing that I just wrote down, and the derivative of that is 2x minus 2. Same answer as they had. I'm not writing down any u's. I'm not doing any substitution. I'm just thinking derivative of the outside, fill in the inside, multiply by the derivative of the inside. Here's our second one. Again, come on. Okay. Again, the book is doing this in terms of use. But it hurts my head even to read that and try to think about how the book's doing it. So I'm just going to explain it my way. Up top in red, I've rewritten the function. Always bringing the denominators up using negative exponents. Always rewriting radicals in terms of exponents. And now, my first step is going to be to multiply 4 by negative 1/2. So I've got negative 2 multiplied by the inside to the power of negative 3 over 2. That's the derivative of the outside evaluated at the inside. And then I multiply by the derivative of the inside. The derivative of 1 is just 0. The derivative of negative 2x is negative 2. And you see that negative 2 and my negative 2 out in front. If I multiply them together, I'm going to get this 4 that they had leading off with. So we have the exact same answer. You can see why the chain rule is going to so often be the mistake that you'll make, right, already. And this is just our first 2 examples. We'll see the chain rule again in practice later on in this video, but now I want to jump into section C, which is about the product rule. So earlier we mentioned this one, true for addition or subtraction. Is this true? If we have if f is a product of 2 functions, is its derivative then just the product of 2 derivatives? Of course not. If it was, we would have mentioned that back in the basics. No, no, no. This is the product rule. And I like the way the book writes this one down. This is how I like to imagine it. That's how I have it in my head. F prime is equal to u prime v plus u v prime. That's the derivative of the first function times the second function plus the first function times the derivative of the second function. And we see we have the exact same thing written down here, just with d's. So dy dx is equal to du dx times v plus u times dv dx. It's exactly what it says in the line above. This is copied and pasted from your formula booklet. So they're going to use the dv's and du's, etc. But other than that, I don't know. This formula is fine. Except a lot of the time, we're going to have to use the product rule with the chain rule. So check this out. Here we have a product. It's square root of x multiplied by 2x plus 1 cubed. And 2x plus 1 cubed, that's the chain rule. So the book is just starting off by establishing what the derivatives of the individual pieces are. In practice, you do not need to do this. You can kind of jump right to the answer. But it doesn't hurt just to note those 2. So let's just take a look at that. The first one should be pretty straightforward. This is just power rule. And the second one is using chain rule. If you're okay with that, we can move forward. Here they're just simplifying what v prime was, whatever. Okay, so now we're going to use the actual product rule. So we're just going to multiply some pieces together. It's going to be u prime multiplied by v plus v prime multiplied by u. So we just substitute those into the formula and we get this amazing expression. How great is that? And we could factor that, I guess, if we wanted to, but there's no real need to. You know, if you were taking the AP exam, sometimes like multiple choice questions will require you to find a particular form for the derivative to be in. For the IB, maybe they'll ask you to show that the derivative of some function is equal to some expression, so you have to do some algebra to get there. But you don't need to simplify every single time. Let's take a look at the second one now. We've got another product. It's x squared times x squared minus 2x to the fourth. And I don't even have room to fit that whole thing here. Oh, there it is. Now, I say that I wouldn't write down all this work, so let's analyze this one to see what I would do. So that's my original function. So I would start writing down, okay, it's going to be the derivative of the first part. The derivative of x squared is 2x, multiplied by the second part. Got it. Plus the derivative of the second part. Okay, let's find that here. The 4 is going to come down for power rule. It'll be 4 times the x squared that's in front. Got that. Multiplied by the inside piece to the power of 3. Still using power rule there. Then I've got to use chain rule. So it's times the derivative of x squared minus 2x. The derivative of that's going to be 2x minus 2. So you comfortably can go immediately from the question to some form of the final answer. Again, maybe you could factor this one if you wanted to, but I don't feel like doing it. You can immediately go there just by applying the rules one step at a time in your head. First think product rule, then in the process of using the product rule, you got to use the chain rule. All right, so product rule is pretty simple. Again, it's just the derivative of the first part times the second part plus the derivative of the second part times the first part. And of course, those orders don't really matter because addition is commutative, so you could easily swap those two around. And then, of course, the individual terms are both products, and multiplication is going to be commutative, so you could swap those two around. You're pretty safe with this one, not likely to get it screwed up. The next formula is the one that's a little bit trickier. It's the quotient rule. This is it from the formula book, although I like to think of it more in terms of what we've got going on up here from our textbook. This one, the order is much easier to mess up because we have subtraction now. And there's still a quotient in the end. So the way that I like to remember this, so that I don't have to keep flipping back to the formula book to check it every single time, is with a little rhyme. Okay, so my original function here is u over v. Okay, so the upper function, the numerator, what I'll call the high function, is u, and then the denominator, which I'll call the low function, is v. So what we have here is low d high minus high d low, draw the line and square the low. Low d high minus high d low, draw the line and square the low. It sounds dumb, but I always say that to myself as I'm writing down my quotient rule or writing down my work to do a quotient rule problem, just to make sure that I get the order really of the numerator correct. I'll never forget that I have to square the denominator. That part's easy to remember, but it's easy to screw up the order for the subtraction. So let's do one. Forgot to cover up the work, but whatever. Let's just jump in. We got a quotient. Looks pretty crazy. Let's do it. So our low is x squared plus 1. Our high is 1 plus 3x. So low d high, high d low, draw the line, square the low. That's kind of what I see happening right here, right? So we've got low times d high. The derivative of 1 plus 3x is just 3. Minus high d low. The derivative of x squared plus 1 is just 2x. Draw the line, square the low. It's x squared plus 1 over 2. This is a great answer. There's not really any reason necessarily to do anything beyond that. If you want to distribute and see if you have some like terms that can combine, great. But in most cases, that's plenty. Letter B. Again, a quotient, low, D high. So I've got low. The derivative of x to the 1/2 is going to be 1/2 times x to the negative 1/2. So that's low, D high, minus high, which is x to the 1/2, D low. D low is going to be 2 times, I don't need to write this down, it's right here. D low is 2 times 1 minus 2 to the x to the 1. That's power rule. But then we use the chain rule, and we multiply by the derivative of the inside. The derivative of 1 minus 2x is negative 2. Putting the negative 2 together with that positive 2, we just get a negative 4 out in front. Draw the line, square the low, so we've got 1 minus 2x to the 4th in the denominator. In this one, I at least immediately see that every term has a 1 minus 2x in it. So, I mean, that's at least something easy to cancel. But again, there's not necessarily a need to. You've got the derivative function. That's all you got to do. Because in practice, what we're going to be looking for all these, and we only saw one example of this in this entire video, is we want to find the derivative of the function at a particular value. So this one might have said, you know, the question might really be, if y is equal to that, what is f prime of, I don't know, 1? Well, we could do all the algebra to get from here to here, and then substitute in 1 in for x. Or, you know what? It's probably going to be easier for most of us just to put 1 in right now. You know, we don't need to do the algebra with all the variables. It's unnecessary. We can just cut to the chase and put the number in as soon as we calculate what the derivative is. The worst thing you could possibly do, of course, is try to put the number in first, because if you just put the number 1 in to this function, you're going to get a constant out, and then you're going to derivative of 0, and it's wildly wrong. Nothing about that process is correct. Maybe some of you were doing that in your head, putting in 1 into this expression down here. You get 7 over negative 2 out. So the slope of the tangent line to this function, when x is equal to 1, is exactly negative 7/2. Great. Now let me show you how we can use technology to work this out even faster. Because if it's paper 2, you are expected to know how to do this. On your calculator, press Menu. We're going to go to Calculus. And the very first option says numerical derivative at a point. That means it's going to tell you the slope of the tangent line to a function at a particular x value. It's really easy. Let's do it. The variable is going to be x. Don't write anything else. The value, that's going to be what our x value is. In the example we were just talking about, we set x equal to 1. So we'll do that. Derivative, this has first and second derivative. We'll talk about second derivatives later on. We're just doing first derivatives right now. So there we go. Now we're just going to have to type in our function. This is great. So we've got the derivative of what I type into this box with respect to x at x equals 1 is something. Let's figure out what it is. I want it to be a fraction, so I'm going to press Control Divide to get a fraction in here. And then it was the square root of x over 1 minus 2x squared, negative 7 over 2. It's pretty amazing, right? That is 100% what you should be doing on paper 2 if you're asked to calculate a derivative at a point. Do not waste time on paper. Do not make mistakes on the paper. Sometimes there's going to be functions that are wildly nasty, things that you wouldn't wish upon your enemies. So use the calculator please. And then one more thing, just notation. You see this like little vertical line here next to the x. So oftentimes you will see it written like that. We could say f prime of x evaluated when x equals 1. That's the same thing as f prime of 1. So I don't know, you might see that on like a website or in a book or something. So there's that. Okay, so look, there's a lot of formulas in this video, and you need to take some time to practice it. Some of the video, especially near the end, once we pass the chain rule, some of the product and quotient rules might have been a little uncomfortable. I might have gone a little bit too fast for you. I'm sorry. Pro tip, just watch the video on 0.5 speed, and that'll slow it down for you real good. If that doesn't work, then just practice some more problems, work out what's going on with the chain rule, and then once you are more comfortable with that and the examples we looked at will be better. Oh, and I promised you I wanted to talk about the multiplication by a constant thing from the very beginning. We said that the derivative of c times f of x should be equal to c times f prime of x, and now we can think about that in terms of the product rule, c times f of x. And of course, the answer is still correct, but let's just look at it. It's going to be the derivative of c times f of x. Well, what's the derivative of c? Oh, that's 0, because the derivative of a constant is 0. Plus c times the derivative of f of x, which, it's exactly what we wrote down over there. So that shortcut really does come from the product rule, but please, if you are dealing with the derivative of a constant multiplied by a function, don't think of that in terms of the product rule. Think about it in terms of shortcuts. We got to use those when we have the opportunity. We'll cut that video there. It's just going to get worse as we continue. There's going to be more and more formulas that we need to keep track of, and they're all going to interact together. I don't even remember if I said this in a previous video or not, but I'll repeat myself. If you ask any calculus teacher on earth, I think, what's more challenging, what's more difficult, algebra or calculus, they're going to tell you calculus is easy, algebra is hard. Each of the individual formulas that we look at here are pretty straightforward, but it's being able to get in there with the variables and use all the formulas together. That's algebra. So if your algebra isn't strong, you are going to struggle a lot through the calculus chapters. So that is why, at least in my course, I really don't take it easy on anybody in the first bunch of chapters. Can't show a lot of mercy, because I know that if I do, and your algebra's not up to it, you're going to get totally rocked. I mean, I've taught AP Calculus a couple of times, and really by the end of the first week, I can say with great confidence who's going to do well in that course and who isn't, based entirely on our algebra review sessions and just assessing how ready each student is to apply algebra to complicated problems. Those who don't know algebra, there's generally no hope for them to actually get into calculus. It's not impossible, but that student would really need to reassess their priorities. More often than not, they don't. But of course, if you've been keeping up with me and working hard, then you're in good shape right now. Stick with me, kid, you'll go far. All right, until next time, go home, practice this stuff. You got to do a bunch of problems. That's the only way you're getting good at it. Peace out.